You know, inside your phone, right now, there's a secret conversation happening. It's this constant, hidden handshake between your device and the cell network. And what if I told you that handshake is controlled by a protocol that can be hijacked? Well, in this explainer, we're going to pull back the curtain on that secret handshake.
It's a pretty scary thought, right? You download some app from the store, it looks totally fine, but could it actually be a Trojan horse? One designed to cut you off from the world, or maybe even worse, listen in?
The answer, believe it or not, is yes. And the vulnerability isn't in Android or iOS, not really. It's way deeper at a much more fundamental layer of how your phone even talks to the outside world. It's all about a proprietary language that most of us have never, ever heard of.
So here's our game plan. First, we're going to start at the crime scene, a real-world flaw. Then we need to understand your phone's architecture, this idea of its two separate brains. We'll trace the private line that connects them, decode their secret language, and then we'll do an autopsy on the hack itself. Finally, we'll zoom out and see how this one little vulnerability fits into a much, much bigger picture.
Okay, let's dive right in. To really get a handle on the risk here, we can't just talk theory. We need to start with a real digital crime scene.
Yeah, this isn't some made-up scenario. We're talking about a real, documented vulnerability, CVE 2020-11292. Researchers figured out a way for a malicious app, one you might just install yourself, to send a very carefully crafted message and get complete control over your phone's modem.
So how is that even possible? I mean, how can a simple app get around all of the phone's built-in security? To get that, we have to look at a really core concept of smartphone design. Let's talk about your phone's two brains.
You see, your smartphone isn't one computer. It's really two computers crammed into one case. On one side, you've got the application processor, the AP. That's the brain you know. It runs Android or iOS, all your apps, your games, everything you see. But there's another, totally separate computer inside called the communications processor, or CP. You might hear it called the baseband. It runs its own super specialized real-time OS, and its only job is to manage the radio, your calls, your 5G data, all of it. And there's supposed to be this critical security wall between them. That separation is supposed to keep things safe. But that brings up a pretty crucial question. If they're two separate computers, how do they talk to each other? Well, let's trace that connection. Let's look at the modem's private line.
They communicate using a system called inter-processor communication, or IPC. The easiest way to think about it is like a dedicated, high-speed, private highway that connects the two brains. It uses things like shared chunks of RAM and very specific rules, protocols, to shuttle messages back and forth. Now, on phones with a Qualcomm chip, which is, a lot of them, this traffic is all managed by a special background process called a daemon, with the catchy name QMUX-D. Think of it as the traffic cop on that private highway, or maybe a central switchboard operator. It takes all the messages coming from the main processor and makes sure they get routed to the right place on the modem side.
And the language that switchboard operator speaks, that brings us right to the heart of our story. It's time to decode the QMI protocol. This is Qualcomm's secret language. So QMI, it stands for Qualcomm MSM Interface. This is the modern, proprietary language that the main processor uses to give orders to the modem. It totally replaced the old-school AT commands, from the dial-up days. It's a really complex, binary system for managing literally everything the radio does.
And QMI isn't just one big fire hose of data. It's actually super organized. It's broken up into these logical channels for different jobs. So you've got one channel just for network control, another one dedicated to voice calls and texts, and a third one for all your GPS data. And remember that vulnerability we talked about? It was aimed squarely at that voice channel.
So what do these secret QMI messages actually look like? Well, they're built from a really simple but powerful structure called TLV. That stands for type, length, value. And this, right here, this is the key to the entire hack.
A TLV packet is dead simple. The type is just a number that means something, like start a phone call. The value is the data for that command, like the phone number you want to call. And then there's the length. It's a number that tells the modem exactly how big the value data is. And here is the single most important point of this whole thing. The modem trusts that length field completely.
Okay, now we know the language, we know the weak spot, we can go back to the crime scene. Let's put all the pieces together and look at the anatomy of this hack.
The entire vulnerability really just hangs on one simple, fatal assumption. As this quote puts it, the modem software doesn't rigorously check if that length field is telling the truth. It just takes its word for it. And this is exactly how an attacker exploits that trust. On the left, you see a normal packet. It says its length is 16 bytes, and it gives you 16 bytes of data. Simple. But look at the one on the right. A malicious app sends a packet that lies. It claims its length is 1024 bytes, but it only provides a little bit of legit data, followed by a big chunk of malicious code.
The result is, well, it's a catastrophe. The modem's processor sees that packet and says, okay, I need to copy 1024 bytes. It sets aside a small space in memory, but then it tries to stuff a huge amount of data into it. That data spills over, corrupting everything around it. It's a classic bug called a heap overflow. And just like that, the attacker's malicious code gets to run directly on the modem, completely bypassing all of the security on the main operating system. Game over.
So that's how one tiny flaw in one hidden protocol can totally compromise a device. Now let's zoom out and see how this fits into the bigger picture, the broader attack surface.
It's really important to remember that QMI is just Qualcomm's way of doing things. As you can see here, other manufacturers have their own proprietary protocols. Samsung uses something called SIPC, which works a little differently. The core idea, though, these two processors talking to each other through some private channel, that's a super common design across the industry.
Now, what happens when things go really, really wrong on your phone? Qualcomm chips have a final fallback. You can think of it like a hardware panic button. It's called Emergency Download Mode, or EDL. This isn't software. It's a recovery mode that's literally baked into the chip's silicon. It's designed to work even if the entire operating system is completely destroyed. And that's what makes it so unbelievably powerful. When a phone is in EDL mode, it allows for direct, raw access to the phone's memory chips. For a repair tech, it's a lifesaver. For a digital forensics investigator, it's the holy grail. It's a way to make a perfect bit-for-bit copy of everything on a device, blowing right past passcodes and any other security the OS has.
And all this leaves us with a really fascinating and frankly critical question. These powerful, low-level tools like QMI and EDL mode, they're absolutely essential for making our devices work and for fixing them when they break. But as we've just seen, that very same access creates a massive security risk. It's this fundamental tension right at the heart of modern technology, and there's just no easy answer. Thanks for watching.